All right. Hello, everybody. Welcome back to Comp 3430 Operating Systems. I hope that you've all had an okay weekend. We're halfway through the term. We are halfway through the term. Yes, yes. Congratulations. There's only 3 more weeks that you have to put up with me. There's only 3 work weeks that you have to put up with my assignments. There's only 3 more weeks of this course. And then maybe your other courses. And then maybe you have a second half of summer. I'm not really sure, but this one is almost over. I hope that you all had a good weekend. I was able to get out this weekend with my family. There's an event that happened that had been happening like annually, and then it started again, I think this year. I don't think they had it last year. It's called Doors Open Winnipeg. Has anybody done that before? A couple people have. It's pretty cool. We went to the Royal Canadian Mint yesterday, and that's pretty fun because you can get a sense of how coinage is made. The Royal Canadian Mint in Winnipeg makes coins for a bunch of different countries, and they were talking about, I think that the current contracts they're making coins for are Canada, but then also they're making coins for the Philippines and also for, I think, Zambia, I think is the other country that they're currently making coins for, which I thought was pretty cool. But on special days like this, they have a gold bar that they put in the gift shop, and there's RCMP officers standing around it, and you just get to go in there and like lift it up. It is firmly attached to the thing that it's supposed to be firmly attached to, but you can lift it and you can feel how heavy it is. And the RCMP officers describe this as it's a $1.9 million bar of gold. And my kids are lifting it up, and like they're having a great time lifting up this bar of gold that they don't realize is like, 10 times my salary for 1 year, which is cool. And then we got to go to the Forks, and there was a nice tour of the Forks that was really nice. In the past, I've been to other places, like the Hydro Building was open one day where you could go and check out the new Hydro Building downtown. And there's a building on, I think it's at the corner of Bannatyne and King, called Art Space. I think it's in that area, and one day you get to go up to the top of the building. You can go on the roof and be on the roof of this building downtown. The event is called Doors Open Winnipeg, and unfortunately it's over now, so I'm telling you about it, and I think it's really fun and it's very cool, but you'll have to check it out next year if you're in Winnipeg. Even if you've lived here all your life, I've lived here all my life, I get to see new cool stuff that I've never been able to see before, and I think it's worth checking out. Let's talk about operating systems. So by the end of today's lecture, what I want you to be able to do is write some code where processes are communicating through message passing via pipes specifically. So we talked about signals last week. I posted some videos to the course webpage in replacement of class time on Thursday last week that go through the idea of writing some code with pipes. And so today I'm not going to write code with pipes, but I do want to step through the code that I wrote in that video. And the goal for that is the second point here. I want you to be able to describe how the operating system supports and implements pipes. So I want you to be able to meaningfully explain things like, for example, how calling the pipe system call adds new entries to the open file table. How calling the pipe system call effectively creates a queue in the OS level, where we can enqueue things to this queue with the write system call, and we can dequeue things from this queue with the read system call. I want you to be able to explain a little bit about how our OS is doing synchronization with this. So how we have a potential process that is reading from one end of the pipe, and it's not allowed to proceed until there's actually data in the pipe for it to read. The other thing I want to be able to do is not really either of these 2 learning outcomes, but the other video I posted was, let's debug pipes. When you're implementing your shell, one of the things that I'm asking you to do is effectively support an infinite number of pipes between an infinite number of processes, constrained within like 250 characters for how many characters is the maximum for a single command, but many pipes. So I want you to support an arbitrary number of pipes. And one of the big problems with pipes and other programs when you call exec is that you can no longer really debug other programs and what they're doing with your pipe. And so I want to show you, just like I did in this video, some of the strategies that you can use to try and figure out what's getting stuck. Getting stuck is the most common outcome of a buggy situation with pipes. How you discover what's going wrong with it, who is getting stuck and why are they getting stuck, using strace, and then solving the problem with pipes in general, specifically with getting stuck with them. After that, I promised that we'd have some time for assignment 2 questions, and I will stick to that promise. So at about 10 to 15 minutes before the end of class, I'll just stop whatever we're doing and we will switch to having questions about the assignment for the remainder of the class. There's 2 other things I wanted to mention just before I forget. One is that I updated the NQP, oh my gosh, I can't even say it, nqpexfat.o file in the template repository for assignment 2. When I compiled this originally, I compiled it with a fairly small size for the open file table in my own code, and I didn't want it to be that small. I wanted it to be very big so you don't run out of file handles without closing them. So I've recompiled it with over 1,000 entries in the open file table. And then I realized after I wrote this message, but without enough time before class, that I actually set up a virtual machine on this laptop so that I could do that. So after class today, I will recompile the ARM version of this. So if you're doing this in a Linux environment on an Apple Silicon, then I'll also have that version posted to you for you up on the assignment template repository. So if you're working with this and you're running into issues where you're getting assertions failing in my code because you've opened too many files, you haven't opened too many files, I just compiled it with too small of a limit. So git pull or just download this file and put it into your directory. The other thing I wanted to mention while we're here is that I had planned originally to return your assignment 1 grades today, but the graders are just a tiny bit behind, so I'm expecting to give it to you tomorrow. I want to make sure that you have enough time to recover if there's something that is a mistake in assignment 1 that you can fix for assignment 2. So please expect feedback for that sometime tomorrow. All right, so let's talk about pipes. When we were sending messages back and forth between processes with signals, we were using a variety of different mechanisms to do this. One of them was like holding control and pressing C on our keyboard, and we were sending the interrupt signal to the process that was currently active in our shell. The other was to use the kill program and passing the signal that we want to send to the process as a command line argument. And the third was to use the kill system call. And it behaves kind of the same way as the kill program does in that we specify the process ID of the process that we want to send the signal to and the actual signal that we want to send to it. But the problem with that whole setup is that signals themselves are very limited outside of different kinds of signals that we could send and previously agree on what their meaning is. Signals can't actually send information to a process. Pipes are a way for us to actually send actual real information between 2 different processes. Pipes are file-like things. Everything that you've done with files in C code is something that you can do with a pipe, with one exception, that in terms of the operations that we've done so far right now. With a pipe, you can read data from a pipe. And you can get stuff off the pipe in the same way that you can open a file and read data from a file. With a pipe, you can write to a pipe. You can put information in the pipe after you've called this pipe system call, and you can work with it as though it is a file. The one operation that you can't really do with a pipe is you cannot seek in a pipe. You can't go to arbitrary locations within a pipe because pipe's data is, the word I'm going to use is ephemeral. So it shows up in the pipe, and when you read it, it's gone from the pipe. It's no longer in the pipe to be consumed by anybody else. When you write to the pipe, it's there until somebody reads it. Once somebody reads it, it's gone. The underlying structure that we're going to take a look at here is that a pipe is a queue. A pipe is a queue. We have upgraded from talking about linked lists to talking about queues in terms of the data structures that we're thinking about in this course. Pipes are queues. The write operation is enqueuing data into the pipe. The read operation is dequeuing data. And when we dequeue the data, it's not on the pipe anymore. Nobody else is going to be able to get access to that. So what I want to do is take a quick look at some of this code that I wrote, and then I want to take a quick look at visualizing this idea of what pipes are doing underneath, specifically in the operating system side. So I'm going to open this up in my terminal, but if you want to follow along with what I've got, if you've already got this repository in your system, you should be able to pull this repository. And if you don't have this repository already, you can clone it using Git. So the file that we're taking a look at here is pipes.c. Is this big enough for you at the back? Awesome. There's some stuff that I'm going to kind of skip over here, but to summarize the intent of this program, the purpose is I want to be able to launch a new process, exec that new process, and then I want to be able to send data to some program that is not code that I've written. Ultimately, that's the goal of this thing. The way that we're going to do that is we're going to create a pipe between these two processes that is shared. And the first and most important line here in terms of working with pipes is line 43. The pipe system call takes one argument, and the argument that you pass to it is an array of integers that is 2 in size. One of these integers will represent a file descriptor that is the read end of the pipe. This is where we're going to be able to call read, the read system call, and use this file descriptor to dequeue data from this pipe. The other integer represents the write end of this pipe. And so this is a file descriptor that we are going to pass to the write system call to be able to enqueue data to this pipe in the system. The pipe system call always has to be made before we call fork. And the reason that we want to do this before we're calling fork is because we're effectively adding new entries to our open file table. Our open file table, remember, this is kind of like a substructure that's in our process control block. And the operation of doing a fork is duplicating our entire process control block. So when I call pipe, I'm manipulating my open file table and I'm adding 2 new entries. When I call fork, I'm duplicating this. So at this point, after I've called fork here, we've got 2 processes. Both processes have identical open file tables. They both have read ends and they both have write ends to this pipe. So their open file tables both contain entries for the read and write ends of this. At this point, the parent and the child are going to diverge in the path that they're taking through the code that we've written. The child is going to be the one that's going to read data from this pipe. It's going to be the one that's responsible for dequeuing things off of this pipe. It doesn't need to enqueue anything. It will never enqueue anything, and I don't want it to ever enqueue anything. And so my strategy here is going to be, I want to take the write end that's in my child process and I want to remove it from its open file table. I want to make it clear that this process will never, ever write anything to this pipe. It's never going to write anything to this pipe, so remove this entry from the open file table for this process. The next thing I'm doing in the child is the child is going to exec, and you can see that on line 72. And once we call this exec, we are never getting control again. But I want my parent process to be able to communicate with this program that I'm execing here. I want it to be able to send data to that program. And so the way that my parent process is going to be able to communicate with that program is to cause that program to have its entry in its open file table for standard input to be replaced with the read end of a pipe. So when we called things like getChar, when we called things like fgetS, when we called things like get anything from standard input, we are ultimately reading from the file that is standard input. Standard input is an entry in our open file table, and it is at stdin file no. Dupe2 is going to take the read end of this pipe, and it's going to replace standard input with the read end of that pipe. So if our open file table is an array, if our open file table is an array, I'm effectively saying copy the contents from entry at pipe ends at 0, the read end of my pipe, and paste it into standard input file no. When I then exec some program later, when it calls read, when it calls getchar, when it calls read on stdin file no, it's going to be reading the read end of that pipe. It's going to be dequeuing data from that pipe because we have previously replaced that entry in the open file table. So when I call exec here, previously we've talked about this as let's replace our memory effectively with this new program. But that doesn't affect the open file table. It doesn't affect the open file table. Things that we've done with malloc previously will get overwritten, but in terms of the open file table, this change that we've just made just before calling exec persists when we get into this new program. So our child process here is now going to start running some other code. And if we are using something like cat here, cat is going to have a loop in it that will read standard input and then print standard input, and then read standard input and print standard input, and read standard input and print standard input, standard output. When it calls read, it's going to get stuck because it's going to be waiting on the read end of this pipe that is its standard input file descriptor. And so it's going to be blocked. It will get put into this blocked state because it's waiting for data to show up on the pipe. Outside of the conditional statement, so this is starting on line 76 here, we're going to close the read end of the pipe in our parent process. Our child process never returns from that conditional block because we've called exec, so we don't have to worry about exit or anything like that. And we're only going to have to worry about the parent here on line 76. On line 76, in the parent process, I'm saying here, I want to remove the entry in my open file table for the read end of this pipe. I'm never going to read from this pipe, so I just want to remove that entry from my open file table. On line 80, the standard input for my parent process is still standard input. This is still my keyboard. I haven't changed it. I haven't manipulated the open file table in any way. I'm just going to read from my own standard input, and this is a blocking call until I start actually typing some stuff in here. Once I've read some data, then I'm going to call write, and I'm going to write to the right end of this pipe. I'm going to send 1 byte at a time. The child process is currently stuck on its standard input, what it believes to be standard input, but is the read end of this pipe. And when I call write, it will get unblocked because there will be data in the pipe for it to read. There's data that has been queued, so it can dequeue that data from the pipe. Eventually, when I have no data on standard input, I will then close the right end of the pipe to tell anybody that's trying to read from this pipe, there's nothing left. I'm not going to send you any more information, and as long as there are no writers left on the right end of this pipe, then the read will unblock, it will return 0, and it will allow us to exit from the loop structure that we've got here. We're a good parent, and so we're going to wait for our child process to finish here, and then we will finish up and kind of exit at this point. That is a ton of me just shouting words at you about code, and the way that I like to think about this stuff is a little bit more visually. And so what I want to do is I want to take the kernel of the idea that we've got here, and I want to try to visualize the structure of what's going on. So the code that I've got here is approximately the same as what we were doing with the code that we've got in this sample. The setup here is that we have a process that started. So the process that started is going to be represented by this code that we've got here. And because it has already started, there is a process control block for this. The operating system has this task structure for this thing. I'm going to omit some of the ideas here, like the context. What is the machine state? What is the program counter? I don't really care too much about those things for this conversation, but they're still there. They are still in the process control block for this process. It does have a process ID, and we've got a system open file table here. And the system open file table, I'm going to represent this in a little bit more of an abstract way than what we have before, to say that the standard input, standard output, and standard error here for this process are connected to teletype 1 or pseudo terminal 1. So imagine this as like, this is the window that I have open for my terminal right now. So when I call read on standard input, I'm getting input from the keyboard. When I call write on standard output, I'm going to send data to be printed out on that specific terminal. So on line 2, after this process has started, the very first thing that we're doing is allocating some memory for some stack allocated memory for a couple of file descriptors. So I'm going to add FDs here, and I'm going to say that entry 0 of FDs is going to be 0, and entry 1 of FDs is going to be 0. When I initially create this array in the first place, I'm just allocating it to have to be filled with zeros here. When I call pipe on the next line, I'm going to do a few different things. Ultimately, in my side, on my user side here, the values in my arrays are going to be modified, and the values are going to represent the 2 file descriptors that I'm going to use for the ends of the pipe that I've got. But what we're going to do on the OS side, when pipe has been called, is I'm going to add 2 new entries to the open file table for this process. I'm going to call them pipe underscore R for pipe read, and pipe underscore W for pipe write. So I'm manipulating the open file table for this process itself. The other thing that as an OS I'm going to do is I'm going to make a new queue structure. I'm going to make a new instance of a queue structure that's connected to the read and write end of this pipe. So I'm going to write the letter Q here because I can't ever remember how many E's and U's and what the correct order is for them in the word queue. The letter Q is good enough. The read end of my pipe is going to be connected to this part of the queue, and the write end of my pipe is going to be connected to this part of the queue. It is a FIFO, first in, first out. When I write something to this queue, the first thing that comes off read will be the first thing that I wrote to the queue itself. Once I do a context and mode switch back to my process here, I'm going to replace these 2 values with 3 and 4. I'm going to change this to a different color. I'll use red here. We're going to change these values to 3 and 4. The 2 values that we have in this array represent the indexes in the open file table for the read and write end for this pipe. We're all good with this so far? Yeah. Pipes will always add new entries to the open file table, yes. Anytime you call pipe, you will add new entries to the open file table. So if I call pipe in a loop for 10 times, I'm going to add 20 entries to my open file table. Any other questions? We're good. We're good. We're good. Awesome. Okay. Our next line here, line number 5, we're duplicating our process control block. We're copying everything that we have in the process control block right now. So I'm going to go over here. I'm going to switch to my copy paste tool. I'm going to change, I'm going to change the process ID for our child. I'll make this 1140. So it has a new process ID. The open file table that we have for our child process is a duplicate of the one that we have for our parent process. And so that means that at least initially, standard input is connected to the same TTY. So I'm getting data from the same place as my parent process. Standard output and standard error, I'm going to just connect these together, are writing to the same standard output and standard error as our parent process. They're both writing to the same terminal. And the two ends that we have in our pipe are also connected to the same place. So the parent process and the child process both have the same pipe entries. They are connected to the same physical queue structure that our OS has underneath to represent the data for that thing. The next line is where we're going to start to diverge. I'm going to do the child process first until we get blocked, and then I'll do the parent process just because it's nicely ordered here for me to be able to do that. But remember that the order of operations here in terms of which of child or parent gets to go first is kind of arbitrary right now. It could be that the parent gets to go first. It could be that the child gets to go first. It continues to look like that until we talk about scheduling. I'm just going to talk about this as though the child process is the one that's going to start first. So our very first operation in the child here is that I'm going to close the right end of my pipe. So that operation here is going to come over, and what we're asking to do with close is I want to manipulate my open file table. I would like to remove an entry from my open file table, please. That operation in our child process will delete this entry. This is close on entry number 4. I want to remove that. And removing that means that there's no longer a right end connected to that queue except for the parent process. The parent process is the only thing that's still connected to the right end of that queue. The next line that our child is going to do is it's going to read from the read end of our file descriptor. The read end of our file descriptor is entry number 3 in our open file table. And right now, this queue is empty. It doesn't have anything in it. And if our queue is currently empty, then our child process is going to block. It's going to get stuck. If our queue is empty, and so there's two conditions here. If our queue is empty and there's someone that has the right end open to the queue, then I will block. Then I get stuck. So I've got two conditions here. There's no data in my queue, and there are writers still available, and that is satisfied right now because our parent process still has the right end open to this pipe. So now we're stuck. We're blocked in the child process. We're going to proceed taking a look then at the parent side. The parent side is going to start here on line 10. And the first thing it asks is, I want to manipulate my open file table, and I want to remove the read end of this pipe. I'm never going to read from it. So I don't need this end of the pipe, and I don't want anyone to think that there are other readers available to write to. So when I call close here, this is closing entry 3 in my open file table. This is deleting that. And when I delete that, I'm going to remove this reference to that read end of the queue. I don't have a connection to that at the system level anymore. The next thing my parent does is it's going to write some data to the pipe. Writing data to the pipe is going to be an enqueue operation. So we're going to move back here to the OS side. And in this pipe, I'm going to say that these two processes are communicating Pokemon, I don't know, Pokemon, they're communicating Pokemon names to each other. And so Pokemon number 1 is Bulbasaur? Oh. There's Bulbasaur. It is number 1. Okay, yeah, Bulbasaur is Pokemon number 1. Pokemon number 1. So I'm going to write Bulbasaur. The transition that we have here is the result of a write operation to that file descriptor by the parent. So quick reminder of where we are. The state that we're in right now is that our parent here has just called write on the right end of this file descriptor, and that operation has enqueued this data to the queue structure that we have in the OS. Yeah?
Since we called fork and duplicated that, does that mean there's 2 separate queues?
That's a good question. The question is, when we called fork way back here on line number 5, did we cause 2 queues to be added? And the answer is no. The only thing that we've caused to be duplicated is the process control block itself. Everything that I've got over here, I'm going to put a line between these with a different color. Everything that we've got over here on the right side of that purple line is not going to be duplicated. Everything between the black line and the purple line, that's going to get duplicated when we call fork. So TTY1 doesn't get duplicated, and the queue structure itself doesn't get duplicated. So I've called this write operation, I've called write, and my child process was blocked because there is a writer and there was no data on the pipe. But now there is data on the pipe. There's data to be dequeued from this pipe. And so the child process here is blocked. It will now become unblocked. There is data for it to consume. Our child process will call read, and it will then remove this. And our pipe will be empty again. There's nothing in our pipe because we called read on it. Our child process will then exit, and exiting of the child process is going to remove its entire process control block, including removing references to those global system things. So we're going to delete everything that we had connected up there when we call exit in the child process. So the queue structure that we have at the OS level right now has one writer open to it, and nobody else is currently waiting or trying to write data to this thing. Back in the parent process, we've called write. Now we're going to close the right end of our pipe. So I'm going to delete this. This removes the right end of the pipe. And now because there are no readers and there are no writers to this pipe, this queue will also be removed from the system level. There's nobody left reading and there's nobody left writing. So there's no reason to keep this around anymore. We can just remove this queue entirely. After that, our parent process proceeds to exit. It waits for the child. The child has already exited. It's no longer in the list of processes or tasks. And so we exit from this and we remove this process control block from our task list. It's no longer running. Yeah.
Can you explain what happens once the parent process writes data to it, and then it gets unblocked from the child process, and then what happens after it gets unblocked from the child process?
Yeah, okay, so I'm gonna undo a bunch of this stuff. There, we're kind of back in the state right now. When the parent process calls write, so that operation has caused this data to be enqueued to the queue structure that we've got. When that happens, the parent could continue to run or the child could start running because the child will become unblocked at that point. I have to emphasize again that I'm just making an arbitrary choice here of, well, now the child takes over because it logically makes sense that the parent is passing this data to the child, and so the child will just start taking that data and running with it. But in reality, the parent could just keep going. The parent could write and then immediately close the right end of that file descriptor, remove that entry from its open file table, and then it will wait for the child and get blocked. At that point, it gets stuck. It's waiting for the child to proceed and finish or exit. When the parent gets blocked, then the child has to take over in this setup because there's only 2 tasks in the system to do anything. And so the child would take over. It would call read, it would dequeue that data, and then it would exit. Once it exits, then the parent would be able to take over again because it's no longer going to get blocked on waiting for the child process to finish.
Since the child process exited, that means it's done and the parent keeps going.
Exactly. Specifically because it blocked itself waiting for the child process to exit. So it gets stuck, and when the child does exit, it is allowed to proceed after that.
So the parent can just continue writing more and more data.
If I had this as a loop structure, so if line 11 was a loop, it would then continue to write more data to this. But in this case, because I have just written one thing to this pipe, and then I've closed, and then I'm waiting for my child, I'm just going to get stuck here. And then once I'm allowed to proceed, I will just exit.
So as you exit, there'll still be data on the queue.
There will still be data on the queue, and that data is important if there are still readers for the queue to have. So the queue structure that we've got on the system side, it's only going to be around as long as somebody holds an end open for it. So our OS is kind of keeping track of how many processes or how many threads of execution currently have access to the right end of this queue structure, this pipe. How many currently have access to the read end? When both become 0, it's no longer accessible, and the OS is free to release any data or any resources that it's acquired, like memory, for that queue structure. Yeah.
So, can you actually see how many messages are in the queue or how many references to the queue there are?
So the question is, can you see can you see how much data is in the queue to be read? Is that the question ultimately? Okay. And then how many references there are to the queue structure? As far as I know, so like take that much for what it's worth. As far as I know, the only way to know if there's data on the pipe is if read returns. Yeah, And if read returns and it returns a value that's greater than 0, that means that there was data on the pipe to read. If read returns 0, then there's nothing on the pipe to read. There's a way to test if there's data on the pipe, but I don't know if you can ask how much data is currently on the pipe. The two processes that are on either end of the pipe, they kind of need to know enough about each other to be able to send the right amount of data. If they're using structured data, so they're sending structures back and forth to each other as opposed to strings, or if they're sending strings, they're just sending bytes to each other at that point. Asking the operating system how many ends of the pipe are currently open, I think you can ask Linux that question, but that's not something that you can just generally do. Yes?
So what if the writing end of it is very fast and the reading end is slow? Overflow?
That's also a very good question. So the question is, what happens if reading is very slow? So if in this setup, the read operation is read 1 byte and then compute pi to 1,000,000 digits, and then read another byte and compute pi to 1,000,000 digits, and then read another byte and compute pi to 1,000,000 digits. So like artificially slowing yourself down lots and lots, or more realistically, being on the other end of the actual fiber that's running across the Atlantic Ocean. I'm going to write data to it and you're going to read, and it's just going to take a long time for you to respond to those read operations. Write can block. It can. It's unlikely to block, but it's possible for it to block. If the queue structure in our OS is full to some arbitrary amount of full, I don't know what the exact number is here, but if it becomes full, then write will block. And we'll get stuck and we will wait in the writing end. Normally this doesn't happen. Normally it's just going to write and write and write and write and write and write, right until there's nothing left to write, and then it stops. But it's possible for it to block. The queue structure can get full effectively. If that happens, you block, and then you wait until there's space for you to write something, and then you write the stuff that you want to write. Yeah?
When we fork the parent, do we actually create new data streams to the queue?
When we fork between the parent and the child process here, we're duplicating their open file table entries, and I'm not sure that I can say with confidence what the actual underlying operating system is doing in terms of counting references to the queue structure. It might be doing some kind of reference counting in terms of this has been called a certain number of times, so there are this many ends open. Am I understanding your question correctly?
Yeah.
Okay.
With like actually closing the file, like it updates like how much streams to that pipe there is.
Oh yeah, so like I'm gonna go way back here. At some point, our OS is going to be able to say, in this situation, for example, that there are currently 2 readers and 1 writer on this pipe structure. Our OS will have to have that information. So it's either going to update that as a count, or it's going to use some other reference mechanism to say that there are 2 reading ends open to this pipe in some process control block somewhere in the system. Yeah.
They're treated differently.
The read end in the parent and the read end in the child are treated as 2 separate things, yes.
Okay, but if it was an actual file, if the child read, you'd update like an actual offset. Now when the parent reads, it's reading from a different position, so they're the same, or?
When we open a file, the file that we're actually adding here is on this side of that division between the process control blocks in the system. So when the child reads, it's going to get the first line. When the parent reads, it's going to get the next line. When the parent reads, it's going to get the next line. When the child reads, it's going to get the next line. So they'll both have entries in their open file table for that file, but the offset is going to be kept at a global system level as opposed to within the process control block for that process itself. Yeah. So if we have multiple readers on a queue, the same effect happens. If process A reads from the queue, it dequeues, and we can't get that data back in process B. If process B then reads from the same pipe, it will dequeue some different data from that read end of the pipe. The difference between a file and a pipe here is that the processes can seek back to the beginning of the file, but they can't seek back to the beginning of the queue because that data is gone. It's already been physically removed from that queue structure.
So I guess reference counts aren't only for like things that have a file system to know how much inodes are being pointed to, but also for that open file table.
For in-memory structures, for the structures that we're creating, we're going to have some kind of reference counting going on for the processes. Yeah. Yeah. Yeah.
Yeah, that's an aside again. So when reading, I guess you have to have some type of message to tell like the child you've read all the bytes, stop reading.
Yes. So the way that you tell the child that you've read all the bytes is that when we return from read, way down here, so this line, I could bring up the source code for cat.c and show it to you, but there's going to be a ton of extra stuff there. But I can promise you that there's going to be a line that looks exactly like this, while read greater than 0. If read returns 0, and that will happen in the case here when I have a read, but there's no write ends open and there's nothing in the pipe. If read returns 0, that means there's nothing left on this pipe and there will never be anything left on this pipe. So you should stop trying to read this pipe. That's the signal that's the way that the message is communicated to the child process, that there's nothing left on the pipe for it to read.
But then I guess when I think of pipes, I think you want to keep reusing it. But then the only way to actually get the child to stop reading is to close it, and then now we can't communicate anymore.
If you want to send more data to the child, then you would have that also in a loop structure. And you'd keep writing and writing and writing to that child process. So that's kind of like what's happening here. I'm reading standard inputs and I'm writing to that pipe. And then I'm reading more from standard input and I'm writing more to that pipe. I am previously going to say, when there's nothing left on standard input, I'm never going to send you anything else. So you should stop trying to wait for data on standard input at this point. If I want to have a long-standing thing, so if I want to have two processes that are open for a really long time talking to each other, then I just wouldn't close that pipe until I know that there's no more data left to send, or I'm exiting or something to indicate that like everything is really, really for real done now. But we could have different pipes open to the two processes communicating different information to each other. So I wouldn't necessarily want to reuse a pipe for two different purposes. I would just have two pipes between the processes. Yeah. Oh, like actually run it. So pipes here, I'm going to run this. TR is translate, and the first argument is this is what I want to match, and this is what I want to change it to. So I want to take all lowercase letters, and I want to change it to uppercase letters. So right now, the state that we're in is we've got pipes. This is the main process. This is the parent that's running right now, and the child that I forked and exec is this one here. So when I'm going to start sending data to this, if I type in hello world and press enter, I'm going to write 1 byte at a time, HELLO space WORLD, and I'm going to send that to that process. TR is reading its own standard input, and it's going to get that data off of this queue structure, and then it prints to standard output. And the state that it's in right now is that it's stuck again on a read. It's waiting for more data because there's still a write end to this pipe that's available. If I press enter right now, when I press enter, I'm sending the new line character. So it's not going to just immediately stop because there is 1 byte that's been read. If I press Control D on my keyboard, that says return from the read call, but don't actually provide any data. Flush the current call or flush the current stream. it will return 0 for read, and then my right end will close because I'm going to exit my own loop. Then TR's read will also return 0, and it will exit its own loop there. Yeah. Because we closed it on our end. In this specific case, I'm closing it here before I'm calling wait, because I want to make sure that my child process exits before I exit. However, if I just exited without closing, the effect ought to be the same. I'm not going to guarantee that, but the effect ought to be the same because my process control block will get torn down because I'm leaving my main function.
Like, as an example, let's say the process or the parent like starts up a child process,
Yep.
and that all it does is it tells you the time. But I want to be able to tell like the child process or send it a command that like tell me the time in a different time zone. But now if the child process has a pipe, and then
Okay.
the only way I could actually send it data is by closing the parent process.
Yes.
And,
Okay. So I'm going to restate this just to make sure that it's on the stream, but also that it makes sure that I'm understanding what you're describing. The problem you're describing is that in the state that we're in here on line 80, the parent process is blocked and also the child process is blocked. But there's no way for me to communicate between the parent and child process because they are both currently blocked. I can't send anything to it. The only way for the child process to become unblocked is for me to send data with write. Once I send data with write, the child becomes unblocked, but then it will immediately become blocked again because it's just waiting for more data and it can't do anything. Does that describe the situation you're thinking about?
Yeah.
Okay. So there's two things that we could do to solve this. One is to start mixing signals into this. Even when we are blocked here on line 80, I can handle signals. A signal can still be sent to me and I will still go into my signal handler if I receive a signal while blocked waiting on input here. So that's one approach that would help us with that problem. The other approach is that we can use another system call, and I guess I want to be clear right now that I'm going to show you this, but it is outside the scope of our course. I'm not going to talk about the system call, and I'm not expecting you to use the system call in any way. There's also this family of system calls that are called pull. So where read will block indefinitely until there is data on the pipe or in the file for it to actually get data from. The pull system call will allow us to say, I want to wait for a defined amount of time. And if there's data on the pipe, I want you to return immediately. If there's not data, I want you to return after 500 microseconds. And then I can do other stuff. And then I can go back to checking to see if there's more data on the pipe. And if there's not, I can do other stuff. And then I can go back to checking. So as opposed to just getting stuck and waiting indefinitely until this happens, we can pull this device. We can ask every once in a while, is there data here for us? And if there isn't, let me do other stuff. So the two solutions that I can think of to describe that would kind of get around what you're thinking of is use signals. Signals are only really going to have an effect on the next time you call read. Polling will allow you to periodically check to see if there's actually data on the pipe to read, and then change other stuff as necessary. All right, okay, cool. I'm delighted that you are all that you're also interested in this. I'm really happy with that. What I want to do is I do want to take a quick look at the Bulbapedia a little bit more. But what I really want to do is spend some time with debugging pipes here. So like I said, I did post this video, but I just want to do it again. I just want to do it again because I think it's important to actually see some of this stuff happening and to try to think about some of the things that you can use to get out of this situation. Pipes are really cool. They can allow us to send more data than we could with signals, but the big problem with them is that they're kind of finicky. They're kind of finicky largely because, we're beginning to work with processes and programs that aren't code that we wrote anymore. When I call exec on cat, I don't know what cat's doing. When I call exec on tr, I don't know what tr is doing. I can't see that source code and I can't enter that source code in my debugger. So how do I get around this? I'm going to take a look at an example that's in this same repository, but I'm going to take a look at the initial state of this. I encourage you to follow along. So if you have a machine that you can do this with, and you have this repository, check out this tag, so pipe still frozen. This takes us back to the original state of the pipes getting stuck in the situation that we're starting to think about here. So I'm going to go back to my terminal. I'm going to quit pipes.c. I'm going to do git pull to make sure that I've actually got everything here, and then I'm going to git check out pipes still frozen. The file that I want to look at here is called frozenpipes.c. Frozenpipes.c does some basic piping stuff here. So I'm going to scroll down a little bit past some of this stuff. And what we're doing here is we're calling pipe, and then we're calling fork, and then our two processes are talking to each other in very much the way that we've been stepping through visualizing this whole idea in terms of what our OS is doing. So our parent process is going to send the child process exactly 3 bytes worth of data. The child process is going to wait for that data to show up. It's going to print it out to standard output. And when it's finished reading, it's going to exit from the loop structure that we've got there. Our parent process is a responsible parent, and it's waiting for its child to exit before it also exits. And then once our child process has finished, that's when we're actually going to go and exit this. So I'm going to change to this directory. I'm going to make this one more time, and I'm going to run frozen pipes. And I kind of want you to take a moment here to just think about what the structure or what the outcome of this might be if you haven't already watched this video. So give you a second to think about this. Line 23 is where we're calling pipe, and then fork. Our child process reads, our parent process writes. The child process prints to standard output. The parent process waits for our child to finish. We got a mental image in our head. Okay, when I run this, we get stuck. And this is a really common thing to happen with pipes. This is a really, really common thing to happen with pipes. The first tool that I pull to when I am doing debugging with pipes is strace. strace is a program that I've shown you once or twice before. And strace will print out all of the system calls that processes are making as they are running. With strace, the last time we used it, we weren't really looking at multi-process stuff. So this time we are looking at multi-process stuff. We're looking at some concurrent code. And so I'm going to add a new option here. The -- follow forks option on strace causes it to attach to new processes every time you call fork. So rather than just printing out for the main process that you've launched, follow forks will then attach to every subsequent process that gets forked off of that main process. When I run strace here, the other thing that I want to do is strace prints a lot of system calls, and there's a lot of system calls that are being made even before our main function starts. And so I want to do a little bit of filtering on the types of things that strace is printing out. These are all documented on the manual page, so I'll invite you to take a look at that if you want to see the other kinds of filters that you want to use. But -e says I want to filter output. Then I'm going to say trace equals, and I'm going to say %DESC. This is going to limit output to system calls that take file descriptors as arguments. I want to limit output to process stuff. So I want it to print out stuff when it's responding to fork, for example. And I also want it to respond to things where it's working with files. So I'm going to say files here. I'm going to hit enter. Maybe it's just file, sorry. Yeah. So I'm going to bring that back. %DESC says system calls that takes file descriptors as input, as arguments. Process is I want you to print out stuff for process management, and file is stuff that, that operates on files and file names. When I hit enter here, I'm going to be able to see kind of the path that this code is taking through the parent and the path that this code is taking through the child. What I really like about strace is that it shows us the actual arguments that have been passed to these system calls. That's helpful for me to think about and reason about what these different processes are starting to wait on. And so I can start to mix like printf style debugging and this to help me figure out what state we're in. So the very first line of output up here is our pipe system call. It turns out that we're actually calling pipe2 underneath, but what we can see here is that the pipe system call is effectively passing back an array to us that describes file descriptors 3 and 4. These are the read and the write ends of the pipe that we have in that pipe system call that we're making. The next line is clone. Fork is not actually a system call on Linux. It's not actually a system call. Fork is instead calling clone. And clone it's doing what we've described. This is the same thing as what we've described as duplicating a process control block. But the actual system call in a Linux system is called clone. After that, we can see that there's two different processes that are starting here. Process with ID 803 here is our parent process, and we can see that it's doing things like writing to standard output, entry 1 in our open file table. This is file descriptor 1. The child is writing to standard output with process ID ending in 4 here. And what we can also see about this is that we have these system calls that are kind of in this unfinished state. That kind of means that the system call was made, but some other stuff started to happen before that system call could actually be finished by the operating system. The important parts here for working with our pipe are here. So this is our parent writing to the right end of the pipe. And this is our child reading from the read end of the pipe. So write file descriptor number 4. This is our right end of the open file table. I'm sending 3 bytes of data. It says that this is unfinished. Then our child process takes over. It's reading 3 bytes from the open file table. And then it also says that it's unfinished. The write returns back in the parent process, and it says here equals 3. I wrote 3 bytes. Write returned 3 here. It says that 3 bytes were actually written to the pipe. Read returns. It says that I was able to read 1 byte from standard input. The parent process writes to standard output. The parent process reads. Then it finishes writing. Then we get I. Then wait. We're blocking in the parent process, waiting for our child to finish. The child process reads the exclamation point. The child process is stuck on read. So we can see that our 2 processes here are each stuck. They're both waiting for something to happen. Our child process is waiting for something to be written to the pipe, and our parent process is waiting for the child process to exit. But in the state that we're in, nothing's ever going to write to the pipe, and the parent is never going to send any more data to this child, and the child's never going to finish because it's stuck waiting for data to be written to the pipe that the parent's never going to send any data to it. In the video, I went through kind of a red herring of like, maybe I'm sending data to the child too early, but I'm not going to worry about that. Instead, what I'm going to say is verbally, when I call write up here, when I call write, I'm going to run this again. When I call write here, the data is enqueued. The system will keep that data until somebody reads it. I'm not going to lose data here. I'm not going to lose any messages between my child and parent process here. The problem that we've got with this code, and the problem that you might encounter as you're working with pipes, is that this read here on line 30 is what we're currently blocked on here. This is waiting until there are no readers or no writers, left on the right end of this pipe. It's stuck because there's somebody somewhere that might have a write end open to this thing. The way that I can communicate to my child process that I have no more data left to send to it is to close the write end in my parent process. I'm not going to send you anything else. I'm going to hit Control C. I'm going to make this. I'm going to delete that. I'm going to make this. And I'll run frozen pipes. And we're still stuck here. And we're still stuck here because when I duplicated my process control block, the child process also has the right end of the pipe. So the state that we're in right now is that just after fork here on line 25, my child process has both the read and write ends open to the pipe. My child process is getting stuck on line 29 because the child process is holding the right end open to this pipe. If there is anyone that's holding a write end open, including myself, then read will block because there's no data on the pipe, but somebody might write to this because somebody holds the write end open to this pipe. If I close in the child process the right end of this pipe, I want to remove that from my process control block. I want to remove that from my open file table. Then it's allowed to proceed because there's nobody on that end of the pipe. I raise this to your attention because when I'm working with a shell, when I'm implementing piping between these processes in my own implementation of this shell, I'm calling pipe n times before calling fork. I'm setting up all of the pipes before I call fork. And that means that every child has all ends of all pipes open. And so in my implementation, I'm going through and closing everything that I don't need. I know which ends of the pipes that I need in my own child process, so I'm just going to close everything. And then at the very end of everything, I'm closing everything in the parent process because the parent process also holds ends of pipes open that it's previously piped before calling fork for all the children. All right, I'm going to post, I've already posted an updated and corrected version of this code up to this repository, so you can find that there. And I will post some variation of this diagram up to the course webpage that's a little bit more coherent than what I've got here, because we're kind of like in this back and forth state. I want to give you a chance to ask some questions about assignment 2. And so I'll hold this here for a couple of seconds, and then I will switch over to assignment 2. But I'm also very happy to answer any verbal questions that you might have about assignment 2.
For the second part, which is the launching processes part, you in the document it said echo and then some text.
Yeah.
Do we need to handle like all of those commands like cat and tr?
Yes. So I'm going to pop up the document because I think that's probably relevant. That will be helpful to this. So I guess I want to be clear here. This is the part that you're describing. I want to be clear that each of these are commands that you will exec. You don't have to implement all those things yourself. You should kind of treat them as general. This is a command that I'm receiving from the shell as input. if you're treating this generally, this is just a string that you're tokenizing. And this is the first argument that you're passing to the read and the write operation that you're working on here. Yeah. So all commands should work, but you're not really going to implement anything differently for each of those commands, if that makes sense.
Yes.
Yeah.
For the commands that need file names, do those file names have to be in your directory?
Yes. So in this case, we're only going to pass input redirection for files because we want to load files from the file system itself. So you're going to replace standard input with this file's file descriptor. You'll read this from the file system and you'll replace the file descriptor for standard input in the process that you're launching. So you can assume that this is the only way that we're going to be passing file names to processes is with input redirection like this.
Okay, and not in any sort of file name, like for TR and the other ones, right?
Yeah, the TR and cat and all of those ones that would otherwise normally expect a file name to be provided as input, you can just assume that we're always going to input redirect for standard input. We're never going to pass an actual file name to them. It will coincidentally work with file names that are coincidentally in the same folder that you're in as the root.image. So if you did cat readme.md, it will coincidentally work and it will print out the contents of the readme, but that's not what we're trying to assess here. It's specifically this case. Yeah. 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 No, I'm putting these quotes around here just to help make sure that it's clear that this is an argument that's being passed, but you don't have to worry about stripping these quotes from anything. You also don't have to worry about complicated cases like the one that I put on the command line here, where I was doing, this one. You don't have to worry about complicated cases like this one. If I'm calling tr, I'm just going to call it with tr a-z to a-z like that. Yeah. Oh gosh, no, 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 I never want to do anything like that. I don't want you to have to deal with cases like this at all. No, 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 no. This is what I want you to be able to do. I don't want you to have to deal with like subshells and stuff. It's going to be, yeah, yeah. Just like this? No. My goal is not to trick you with edge cases. The thing I'm assessing here is process management and piping, and I don't really care for you to actually implement a shell. If you want to do that for realsies, please have fun, but do it at a different time than right now. Do it at a different time than right now, and then tell me about it later because I'd love to see your shell. But yeah, I'm not looking to trick you with edge cases here. I'm going to pop over to this. And I can see that lots of people have answered this question, so good. And it is hydraulic action. And yes, I'm sure that their brains are involved in that somehow. But I will take further verbal questions. Yes? Can I, within our shell? No, I don't want us to create files because then we'd have to have write support to our file system, and I don't want to do that. I don't want to do that, and I don't want you to have to do that either. Yeah, okay, good. I'm glad that we agree. Could we have test cases where we have multiple pipes to test if our code works with it? For sure. I can add these to the README later, but here's one. Cat, 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 cat. Like this. This is one long case of lots of pipes, and this will just print out to standard. If I could type, that will just print to standard output once. I could do something like cat, 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 and I can stick a tr in here, tr a to z like this, and it's the same sort of thing. So print to standard output. This will print to standard output if I hit Control D here a bunch of times. Yeah, those are two examples that we could use for this. But I can add some more later. I can add some more to the README. Okay, so we don't know who runs first, the parent or the child. The scheduler changes between the parent and child when they are blocked. Okay, so that is true. That is 100% true. Again, my strategy for this is I'm going to make all the pipes in my parent process, in my shell. I'm going to make every pipe in my shell. And that means that when any child process runs and it starts to call read on the read end of a pipe, it will get stuck. It will block because nobody has written to it yet. It's only going to get started when the thing that's on the very far left side actually starts to call write on the right end of its pipe, that the rest of the pipeline will be allowed to flow. If you are like making pipes as you're making processes, it's going to be harder to make that happen. And so, like I said, my strategy is make all the pipes to begin with so that everybody gets blocked on read as the reads are getting called here. Directory changing is essentially saving the prefix of the path somewhere. Yes. So if you're changing directory to some other directory, then it's effectively saving that prefix. I would strongly recommend that you use a stack to implement this. So as you change into a directory, push something onto the stack, and as you change out, pop, as opposed to doing string manipulation, because dealing with string manipulation is painful at best in C. How to modify the makefile to compile that too. So if you want to have your own implementation of a stack here, what I'm going to suggest that you do is if you've got NQP underscore shell like this, you can say that this depends on stack.o. And if you add that and your file is named stack.c, it should also then compile stack.c to become stack.o and then allow your shell to compile with that. I think I answered that when I was answering your question, but ultimately cat is never going to read an actual file. It's just going to read from standard input, and standard input will be replaced with a file descriptor for some file that we previously opened. So we're only ever going to use cat with actual standard input or a file name, a file that has replaced its standard input. In this case, like I said, I'm not trying to trick you with edge cases. So you can just assume that there's going to be one space after CD for when the graders are working with this. The commands that we're going to be assessing are in the root image itself. So that's kind of where you could start. Then the 3 built-ins are described in the assignment document. Yeah, you can 100% use my implementation. Like I said, I'm going to post an ARM version of the exFAT reading code on the course website after class today. But the one that's up there is updated, and you should be able to use that for sure. I really do think it's cool if you can use your own, but you're not required to use your own for this. And that's it. Okay, awesome. All right. So I will have some more time for questions on Wednesday if there are any more questions. But at this point, you should be able to write code where processes communicate through pipes, and you should be able to describe the operating system supports to implement pipes. That's it for today. Thank you for a few extra minutes of your time, and I will see you all.